So I will present you the 3.5 optical sources for high bit rate fiber transmission. So let me give you an overview about the Almae technology, which Almae Technology was founded in 2016 as an industrial spin-off company from 3.5 lab. So in Almae, we design and manufacture indium phosphide based high speed laser integrated photonic chip to address the new generation of telecom and datacom application. So in terms of facilities and portfolio in Almae, we have 2 clean room. The total we have 1,700 square meter. In terms of epitaxy, we have different reactor, MOPVP and MBE. And especially for our main topic, it's the photonic integration. And we have a building block. We involve the budget growth technology. We have the E-beam grating fabrication process and the ACBH growth, especially to improve the performance and the lowest power consumption. So, in terms of product development in Almae, we have typically the EML laser, especially used for the long distance reach. Here you see the building block, which involve at least 5 growth steps, the E-beam grating, and typically this kind of devices take at least 6 months of process flow. So we have product for the 10G EML at 1.155 with the extension ratio around 10 dB and the high power over than 6 dBm. Also in terms of EML, we have also the 25G and 50G. Here we have the PEM4 for the 50G and at different temperature, 45 degrees, 55 and 60 degrees. Also, for the high output power technology, we have different technology with the rich waveguide and with the ACBH technology. It's what we will use for the MASSTART project. So right now we will discuss directly about the topic of datacom. As you know, the explosion of internet traffic driven by the mobile devices and cloud computing show faster growing of data traffic faster than the system capacity. As you can see here in this figure, in 2015, the traffic was around 4.7 zettabyte. It's 1 zettabyte, it represents 10 billion terabyte. By 2020, the global annual traffic will reach 15 zettabyte. So to put things in perspective, it represents enough data to fill stack DVDs that will stretch from Earth to Moon and back. So in this figure, you see that the 77% of the data traffic it represents within data center, especially for the short distance. We can address this by the DML25G. The 40% it's represented by data center to user and data center to data center. Here it's for long reach distance. Typically we use the EML25G or 50G. So what we have to know that if you want to address this market, we can address it by two technology. We can provide the high output power and integrate on the photonic platform, or to develop directly the 3.5 component like EML25G, 50G, or DML25G. So in framework of MASSTART project, the The objective is to to address the next generation of transceiver and to massively use the silicon photonic based PICs. So in Almae Technology, we have to develop the new laser chip design for low power consumption and long-term reliability demonstration. So here is the platform where we will integrate our laser array. We have different demo. We have demo with 4-channel PSM4, demo 2 for 8-channel WDM and 16-channel WDM. So the challenge here is to provide high output power with in-cooled operation and with to manage the coupling efficiency. Thanks to our technology in Almae, we have two technologies, the ridge waveguide and the SCBH. As explained before, the ridge waveguide is limited in terms of coupling efficiency. We have high output power in-cooled operation, but it's not adapted for the photonic integration. The second technology that we have is the bird heterostructure that we as you can see here. Thanks to this technology, we can reach low capacitance, spot size. We can integrate the spot size converter, and we can easily manage compensate the losses in terms of coupling. We know that especially for the photonic integration, it's very important to manage the coupling losses. And the third parameter, it's the low consumption for the ACBH technology. It's more efficient for the photonic integration. It's what we have used for the MASSTART project. The second thing, it's the e-beam grating. It's very important given that we have to address different channel. We have to get very accuracy wavelength. Thanks to our e-beam tools, we can have accuracy less than 1 nanometer, which is very useful for this application. So now, in terms of material laser that we for the development, we have focused our work on the aluminum-based quantum well, especially because we have for the in-cooled operation we need to have very high confinement for the electron. So for the standard system material, gallium indium arsenide phosphide, the confinement is very low for the electron. When we increase the temperature, you can see the overflow of the carrier. If you compare with the new material based on aluminum, we can improve easily this confinement, and we can reach the in-cooled operation. It's what we have to do especially for the demo one. Now, yeah, because we were interrupted. Sorry for that. Can I continue?
Yes, please.
Yeah. Okay. As I said before, for the aluminium, at the beginning when we start the project, we are limited in terms of output power because we have had really high leakage current, owing to the interface in the sidewell. So we tested different configuration. We integrate a PNP regrowth instead the ACBH standard ACBH regrowth. And thanks to this configuration, we have improved widely the characteristic temperature. In 2019, we had around less than 40 Kelvin. Right now, we have around 78 Kelvin, which is a very high value in order to reach high. So with the new system material based on the phosphor material, we have shown here very high output power in-cooled DFB with low ATH and high output power. It's what we have used for the demo 1 and demo 2, as we can show you here in terms of results. For the demo 1, the target was to have 4 channels for in-cooled operation till 85 degrees. And for the demo 2, it's 8 channels with the temperature operation at 45 degrees. So right now, currently, we have developed new generation of high power DFB when we have increased the output power at high temperature by 25%. It's what we intend to apply for the next devices that we will develop in MASSTART project. Up to now, I have shown you our development for the high power DFB that we can include on integrate on the photonic silicon. As I said before, we have the 3-5 components, high speed laser. Here I show you the 1577 nanometer 10G. Here you can see that here is the distribution of the devices on the wafer. Most of the devices has more than 6.5 milliwatt. And in terms of the extension ratio, we are more than 13 dB.
Yeah, I suggest that we move to the next presentation, and we can recap at the discussion session with Sofiane and address any questions when hopefully he has a better connection.
Yeah. Please feel free to send me any question by email.
Yes. Well, it seems that you are actually online now,
Yeah.
and it seems that the audio is better now that you're not sharing your screen. So maybe we actually got one question regarding the advantage of the aluminum gallium platform for the quantum wells over the other material, given that it does not increase the output power. There's a question on the chat.
So the aluminum-based multi-quantum well, it's very interesting because we have the confinement for the electron. It's 70%. We have 70% confinement in the electron and 30% confinement for the holes. Thanks to this confinement, we can improve widely the high. We can increase. We can improve the operation for high temperature. Is for this reason the aluminum system material is very interesting for the in-cooled operation if you compare with the standard material phosphor based.
Thank you very much, Sofiane.
You are welcome.
Thank you so much for the very interesting talk.